95 5b Luke showed that if a particle is dropped down like this and rebounds horizontally, then the tan of beta is equal to root e. First thing I'm looking at anyway is the angle there is beta, and alternate angles mean that that's beta as well. I've drawn in a normal, so the angle between the normal there and the plane is 90. So if that's beta, that's 90 minus beta, so that's beta as well. And the idea here is, because there's a beta in here and in E, I want to see, can I have betas, the angle beta between my U and between my V, and then I can link the two. So that was idea one. Idea two is you need to rotate the plane. So the plane itself needs to be rotated through an angle beta. So that's what I've done there. Everything else then is rotated as well. So that was falling down. If I rotated the plane, it would go like that, down like so. The ball then bounces off at right angles, so it bounces off like that. And again, we've got beta, alternate angle beta there, 90 minus beta, beta, and an alternate angle of beta there. So once I have this, then what I'm thinking of is get my U, my vector U in I and J form. I'm then thinking, what stays the same, what changes? So because the plane is horizontal there, the I component is going to stay the same. So the I component stays the same afterwards, and the J component changes. Now what you'd be doing there is you'd say that the velocity afterwards is equal to minus E times the velocity before. So I've just taken that velocity, multiplied it by minus E, and it gives me that thing. Alright, so we have the velocity after, right? And because we're looking for tan of beta, and tan of beta needs to involve an E, and because I've got betas here, and because I got beta with the final velocity vector as well, and more importantly, I need an E in the equation, I need to use the V thing. So to put that briefer and a bit quicker, because we want to relate tan of beta to E, there's a beta in the initial velocity vector and a beta with relation to the final velocity vector. But because we're looking for an E to relate to the two of them, I need to pick the final velocity vector. So tan of the angle will be the J component over the I component. We take the absolute value. U's cancel. Sine over cos is tan. Cos over sine is 1 over tan. And then cross multiply, get the square root, and that part is done. That's the first part. The second part then involves the kinetic energy. And like so many questions in applied maths, what you need to be thinking of is the second part will rely on the first part. So, let's see if we get a bit of focus there. Tan beta is root E, so tan beta is root E over 1. Draw a model triangle. Tan is opposite over adjacent, so opposite is root E, adjacent is 1, and use Pythagoras to get the hypotenuse. Once you have that, then we'll be getting the sine and the cos. And the reason for that is because the fraction of kinetic energy lost formula, which is the kinetic energy before minus the kinetic energy after, divided by the kinetic energy before. The U and the V are the speeds, so they're the magnitude of the velocity vectors. Look, the half and the m's cancel, you can see that. And what I've done there is I've divided the U squared into the first and the second term to give me that form of it. Now remember, they're the speeds. We already know that the speed of U is actually just U, so we need to get the speed of V. So I've taken the V vector, and to get the magnitude of it, I've got the square root of the I component squared and the J component squared. It gives me that. Take the sine and the cos from that thing above, sub them in, take out a common factor of E, and we get the speed there is U by root E. Now we sub that in as the speed there. We know U is U, and we end out with 1 minus U root E all over U to be squared. Gives me what we're looking for.